Alright everybody, welcome back. Today I'm going to walk you through a step-by-step guide of how to plan a VFR cross country. So the route we're going to plan today, we're departing Stratford and heading up to Hanover, and we're going to do a set heading point over Milverton, and this will be the route that we're planning. So we're going to fill out our nav log and figure out our time and fuel required for the flight. And I hope this is beneficial for you. So let's get right into it. We're going to start with all the map planning first. So to start, you'll lay out your VNC map, have your pencil ruler ready. If at any points you need to pause the video to catch up, that may be helpful for you if you're working through this together. So we're first going to start just by looking along our route and taking into some considerations such as restricted airspace. If there is other aerodromes we're flying over top, so we want to have a good look along our route, and that'll help determine a couple of things: our set heading point, as well as the track. If we need to avoid certain airspace, like restricted airspace down in this area. You can also take into consideration any radio nav aids that you could use. Nothing really for this leg. Once you've had a good look and you've determined your track, we can see Stratford's down here in Hanover. We want to pick a set heading point that is efficient. So Milverton just takes us a little bit slightly off a direct path. So it's also nice and close. It's within the 15 nautical mile range. So looks like a good point for us. So I've selected Milverton for the set heading point. We're going to visually fly to there, and then we're going to begin our tracking from here. So step number one is going to be to draw your track. So take your pencil, your ICAO ruler, draw a nice straight line from your set heading point to your destination. And it's going to look something just like this here. So this first section is the climb out, and then here's our planning leg. Step number two is going to be to draw 10 nautical mile marks. So measure out 10 miles on your ruler. Make sure you're using nautical miles and not the statute mile side of the ICAO ruler, and put a mark on the map every 10 miles. You can also use these lines of longitude for scale. So 10 miles would be from the bottom to this tick here. Next, you're going to mark out your halfway point. So make the halfway point a large visible line. You don't want it to be difficult to read while you're flying. So do a nice big thick line for your halfway point, just like this. And now we're going to determine our track. So if you take your, this is on a VNC. If you take your protractor and put the very center of the protractor on the midpoint of your track, it's important that you're measuring from the midpoint on a VNC. And then you're lining up the black lines parallel or on top of a line of longitude. So you can see from the top to bottom, it's pretty well parallel here. And then we read the track and the direction we're going, which would be right here. It looks like about 351. So this is our track in degrees true, and we can note this down on our VFR planning log. So here's the VFR planning log. We can start to fill this out. We'll go from CYSA, CYHS, and our true track, we said 351. Alrighty. The next step, so we've figured out our track. The next step is to draw our 10-degree drift lines. So now go from your set heading point and line the track up on north, and just put a little tick left and right 10 degrees, both from your set heading point and from your destination. And then you'll draw your lines. I like to do dash lines, and it's going to look like this on your map. So those are your 10-degree drift lines used to help navigate. Next, we're going to determine the variation. So your midpoint variation, your lines of variation. Here's one here. We have 9 degrees west is a dash line. We have one to the right here, 10 degrees west. So we're kind of in the middle. Let's say 9.5 degrees west is our variation. If you're having trouble finding those lines, normally in Ontario, or if you're around a body of water, if you look over the lake, they're going to be very easy to find. So here's your 10 degrees west, 9 degrees west, and so on. As you look over, they're a lot easier to pick out over the water, and you can just follow it up. So we're going to come back to our planning log. And we're going to put in our variation, 9 degrees west. Alrighty. Next, we want to look along our route and determine our minimum altitude that we could fly at. Couple ways to do this. You can look at your maximum elevation figures and read the center number. That's going to be the highest obstacle within that entire box. Within this entire box here would be 2,100, but it may not be close to your track. It looks like along our track, these towers are a lot lower. Over to the right, here's 1930. Looks like a windmill. So you can scan left and right of your track. Looks like 1,500, 1,600 here. We want to check out our destination as well. 1,800, 1,850. But a nice quick way is take your highest maximum elevation figure and add 500 feet. So 2,700 would be our minimum obstacle clearance altitude for this leg. So we can't be any lower than that, essentially. We'll also keep in mind, if you were flying over any uncontrolled aerodromes, you want to be 2,000 feet AGL. So, there's a restricted one here, Fordwich. Here's their elevation of 1,250. So 2,000 AGL would be 3,250 indicated altitude. For that little aerodrome, there's Wingham is an uncontrolled aerodrome over here, which is, we're far enough away from that one. So keep that in mind as well. A couple smaller ones at Listwood here. We want to be 2,000 feet above any uncontrolled airports to make sure you're not flying through the circuit. We can determine, so we figured out our lowest altitude. Let's determine the altitude we want to fly at. And that's going to depend on a few things. We want to take into consideration definitely the VFR cruising altitudes, which are based off of the magnetic track. So if we take our true track of 351 and we add the variation of 9 degrees west, we actually end up right on north for a magnetic track. And the cars say from north to 179, it has to be odd thousands plus 500. So that would be 3,500, 5,500, 7,500. And then from south to 359 would be even plus 500. So we actually we're right on north. So we just fall onto the odd plus 500. And now we can take a look at the upper winds and see if we can use we want to obviously avoid a headwind and try to take advantage of a tailwind. So this will come into play when we're determining the height which we're flying at. So here's the upper winds. I'm just on the aviation weather website, the upper winds. I'm going to go below flight level 180 for Ontario and Quebec. And Wyerton has upper winds, Toronto has upper winds, Windsor has the upper winds. We could interpolate between them. For today's sake, I'm gonna say we're flying within this time slot from 17 to 21. And we'll look at the winds from at 3,000 feet, 320 at 9 knots, 6,000, 320 at 15, and 9,000, 310 at 22, and the temperature is minus 19. So I'm going to write this down. We're heading to the north, so we're going to have a little bit of a headwind. It looks like if we stay a little lower, it's going to be lighter winds and a little from the west, so it's not as much of a headwind. So I don't want to go to 5,500 because I'm into a headwind with stronger winds. So I'm going to stay at 3,500. That's above my MOCA. And the winds are 270 degrees true at 9 knots. And I'll also write down the, we said we were going to use the 17 to 21. So everything is quite similar, but we're going to be 230 at 9 knots. And I'll write down the 6,000 just to have them as well. So we'll be using that temperature later on. So the 6,000, 320 at 15, temperature's minus 18. They don't give a temperature at 3,000 feet because it's influenced too much by the ground. So let's go back to our nav planning log here. We're going to pick our altitude. $3,500. Okay, so we got our altitude there. Next step, or the last bit of map work we're going to do. So right now your map will be looking similar to this here. So you have your track, you have your 10 nautical mile marks, you have your halfway point, and you have your 10-degree drift lines. We need to pick out ground speed checkpoints, and then that'll be the last step of our map planning. So normally towns or very recognizable landmarks work well for your ground speed checkpoints, and you want to get one within the first quarter of your leg. It looks like after Milverton we have the town of Listowel we're going right over, so that would be a very good ground speed checkpoint. Something I wouldn't use would be this tower, because it's very two-dimensional. It's hard to distinguish this tower from that tower or that tower from that tower. If you can use three-dimensional points such as towns and intersections of roads, if there's a T in the road or a large bend, that's going to be very easy to recognize. So let's use Listowel. We're going to measure the distance from the set heading point to Listowel and the distance remaining from Listowel to the destination, and record that in our en route nav log. So using the ICAO ruler, we'll look at our flight log here. We're going to put in Listowel, and right here is where I like to record the distances. So from the set heading point to Listowel, I had measured 11 miles, and the remaining is 25. And we'll do the same thing at the halfway point. which our was 18 and 18. All right, so this is going to be used for in flight. We'll talk about that towards the end, how we use these to establish our actual ground speed and then revise your ETA to the destination. One other thing we want to do is measure your total distance here. So just from your set heading, this will be from the set heading point to the destination. And I measured that to be 36 miles. So this is how we have our nav log setting up. All of this information we've done so far can be done well ahead of the flight. It's not going to change. All of the stuff remaining is going to be done either the evening before or the morning of the flight. So let's get into more of the weather and the performance calculations of the cross country. What I'm going to do is just use the latest weather out of Kitchener if we're departing Stratford. So coming to the aviation weather website. And I'm going to use the current weather here. So currently the altimeter is 29.91. And it's been pretty stable the past few hours. Okay, so we're going to work down this column with the weather. So the altimeter setting, 29.91. Our pressure difference, we take the standard pressure, 2992, take away our current, and it's 0.01. Cruising altitude, 3,500 feet. Now our pressure altitude is going to be the pressure difference times 1,000, because the altimeter setting is in thousands of feet. So if we do 1,000 times 0.01, it is 10. So our pressure altitude becomes 3,510. Now, if this was a negative value, if our altimeter setting was 0.93, this would be a negative 10, and we'd subtract that. The temperature at 6,000 feet was minus 18, and we're 3,000 feet below it. So I'm going to say that's 3 degrees, or 3,000 feet. So 6 degrees warmer is going to be about minus 12. Minus 12 here. Yeah, I'll put the wind velocity up here. So we said at 3,000 feet, it was 270 at 9 knots. Okay, the density altitude. We'll calculate this with the E6B. So we have a temperature of minus 12 and a pressure altitude of 3,510 feet. So if you get out your E6B, we'll come to the front, and we're going to be using this column here. So we have the temperature, your air temperature. We said it was minus 12. And we'll line that up with a pressure altitude of 3,500. So it's 1, 2, 3,500 is right in the middle. It's that's minus 15, minus 12 would be right around there. Would be right around there. And then our density altitude is going to indicate right in the middle here. It looks like it's just over 1,000. Let's say 1,100. So a very low density altitude, and we can expect good performance. So that is a good thing. Gives us an indication of the aircraft performance. All right, now we're going to look into the POH, determine our RPM, and our power setting. So here's your cruise performance chart for a 172. If you read the normal cruise procedure, it says normal cruise is conducted between 55 and 75% brake horsepower. So I generally always go towards 65% brake horsepower. Now we need to determine, are we 20 degrees below standard? Are we standard, or are we 20 degrees above standard at cruise? So if it's minus 12 at 3,000 feet, we want to compare what it would be at standard. So on a standard day, sea level is 15 degrees Celsius, and we lose 2 degrees every 1,000 feet. So we're going to lose 6 degrees for 3,000 feet. So 15 take away 6, we have 9 degrees above zero on a standard day, and it's currently minus 12. So the difference between minus 12 to 9, 12 to 0 is 12, and then 0 to 9, we're 21 degrees below the standard. So we're going to use 20 degrees below standard, which would be this column, and we're going to use our pressure altitude, 3,510 feet. So we want to be, the numbers are going to be 3/4 closer to the 65 here. So if we look at 2400, it's 69%. 2400 RPM is 65 here, which is a difference of 4 horsepower. So if we take 69, take away 65 is 4. And if we said 3,500 is 3/4 of the way to 4,000, so we're going to take 3/4 of 4, which is 3, and we're going to subtract it because we're getting lower from 69. Subtract 3 is 66. So at 2,400, we're going to have a brake horsepower of 66, which is pretty close to 65. I'm happy with that. So that will be our power setting here. So 2,400, and your percent power, 66%. So for that power setting, we're going to figure out the fuel consumption. So 2,400, we're 9.1 and 9.6, a difference of 0.5, so it's going to be 1.25. So we're going to come to a 9.225. So we'll call it 9.2 gallons an hour. All right, now we're going to figure out the true airspeed. Same column. 2,400 is 110, 105. So it's going to be 109. And we'll also stick it up here. 109. All right, we'll figure out our calibrated and indicated airspeeds next. So to go from our true to calibrated, we're going to have to go back to our E6B. And you want to set it up for your density altitude, so I haven't moved it. It's still set at the density altitude. The outside is your true airspeed, which we said was, what did we say that was? 109. So we'll come to 109 on the outside. There's 109. Straight down is 107. So that's your calibrated airspeed. One 107. And the indicated airspeed is going to be the airspeed correction chart in your POH. So make sure you're on the normal static source. For flaps up, if we have a calibrated airspeed of 107, we go straight up to an indicated airspeed of 110. Awesome. All right, so a couple more things left to do here. We need to figure out our heading, the ground speed, and then our time and fuel. So the heading, we're going to go to our E6B and we're going to need the wind and the true airspeed. So a true airspeed of 109 and then the wind 270 at 9 knots. And we want to use the backside of our E6B here. So the steps for the E6B, first you want to set wind direction under your true index. So the wind direction was 270. So I'm going to spin this to 270 and mark wind velocity up from the center point. So if I put 100 under the center and then the wind was 9 knots, so I'm just going to mark up 9 knots from the center point right here. Then we set our true course, which was 351 underneath 351, and then slide wind velocity mark to your true airspeed. So the true airspeed was 109. We're going to slide our blue dot down to 109. And then the ground speed reads under the center point. So our ground speed looks like it is 107. And then our heading, if we look over, so 10 degrees is here. So it'll be 2, 4, 5 degrees to the left. So from your true index, come over 5 degrees straight down. 3, 4, 6 is our true heading. Three, 4, 6 plus 9 degrees west. If you remember the saying, west is best, east is least. 3, 4, 6 plus 9 is going to be 355 for a heading. Our ground speed was 107. And we can figure out the fuel and time. So ground speed of 107, a distance of 36. We'll come back to our E6B. Come to the front side of the E6B. It was a distance of 36 and a ground speed of 107. So we're going to put this black diamond onto 107. And the outside is our distance, the inside is our time. So a distance of 36 on the outside, 35, 36, reads 20 minutes on the inside. So our time here, 20 minutes. And the fuel, we're going to need our 9.2 gallons per hour. Come back to the E6B, and we're going to move that black diamond to 9.2. Go to 20 minutes on the inside and read straight down. We'll go to the next tick up, and we're 3.2 gallons. .2. There we go. So that's that leg planned. Just a couple more things that we have to add in here. I always add in fuel for the circuit. And I add we'll add 5 minutes and 1 gallon of fuel. 1 gallon. Alrighty. We can also add in our reserve we need 30 minutes of fuel at cruise. So cruise is 9.2. Half of that is 4.6 gallons. So that's what we need to have on board for reserve is 30 minutes at cruise, day VFR. And I like to always add in contingency. Just any extra fuel you want to carry on board to deviate for weather. Maybe the airport gets closed if you're on your way there and you need to divert to another aerodrome. So I'm going to say I want an additional 30 minutes. Just for contingency. So it'll be 4.6 here. All right. The last thing is our taxi run up and climb fuel. So how much fuel do we need to climb up to 3,500? Once again, we have a chart from the POH, time, fuel, distance to climb at max gross. And we're climbing out of Stratford. The elevation is 1,200. So the pressure altitude, we'll make it easy, say it's 1,000. And we're climbing to 3,500. So 3,500 is going to take 5 minutes. And but we're starting from here, so we'll subtract 1. It's going to take 4 minutes in the climb. 4 minutes in the climb. 1.4, subtract our 0.4, it's going to be 1 gallon. But we also have to add, if you read note number 1, 1.4 gallons of fuel for engine start, taxi, and takeoff. So your total is going to be 2.4 to start, taxi, takeoff, and climb. And then the distance it's going to take is 9, take away 2, 7 nautical miles. Now that's an important one because if we take a look at our map here, this, we would measure out our climb leg and see how far it is. So it's going to take us 7 miles to climb, but if our point was 20 miles away, we only calculated this part of our fuel in the first leg. So if you're having a set heading point that's further away, let's say it was 20 miles away, we're only going to take 7 miles to climb, and that's the fuel for the climb. So you're going to have 13 miles of no fuel accounted for there. So you must include that fuel if you get to your top of climb prior to your set heading point. So that's important. Don't forget to add that fuel. But let's put in what we did calculate here. Mine's right around 7 there, so that's going to work out. So our taxi this is going to be 4 minutes, 2.4 gallons. So our total fuel for departure, we need to add all this up. We have 3.2 plus 1 plus 4.6 plus 4.6. Comes to 15.8 gallons. And our time en route, we're not going to include, if we're using this for a flight plan time, we're not going to include the reserve or contingency. We're only going to include the time we're going to be doing. So it's going to be 4 minutes for the climb. It's going to be 20 minutes to get there. We're going to be 5 minutes in the circuit there. So 29 minutes from wheels up is our estimated time of arrival. All right, so we figured out all this information. We could transfer it over to this line. We do our flight altitude, true airspeed, your track heading, your compass deviation from the compass card to get your compass heading, the distance and your time. So 36, 29 minutes. And that is going to be our planning. A couple quick mentions here about the flight log. So as you're flying along, your time over Milverton, you're going to record your time. That you won't have an observation or ground speed, but your ETA will be this time, 29 plus time over will be your first ETA to Hanover. And then as you're flying along, you get over Listowel, you record the time. So let's say it took you 7 minutes to get to Listowel, and that's 11 nautical miles. So you're going to calculate your ground speed with the E6B. So you're going to line up 7 with 11. 7 is the time on the inside with 11. So ground speed in this example, I'm just naming off numbers, is going to be 94 knots. So you would record your ground speed. And then you would keep the wheel the same, go to 25 on the outside, and it's going to be 16 more minutes. So if we go back to our flight log, we're going to have an actual ground speed of, let's call, we said 94. And I'll just make up a time here. I'm just going to say 11. If we were over at 11 o'clock, it'd be an additional 16 minutes. So your new ETA is going to be 11:16. So we've revised our ETA. And then once again at your halfway point, if it took you 15 minutes to get from your set heading point to your halfway point, it's going to take an additional 15 minutes. So you could revise that ETA to maybe 11:20 or something, whatever it would be. But if it was 11:16, then at your halfway point, if you were over your, always go off your original set heading time, and the time from there, it's going to be the exact same because you're halfway there. So that's going to be more your flight log while you're in the plane flying. That's what you do, just as an example there. But that's how you fill out a VFR nav log. Additional stuff you want to do is read up on the CFS about the airport information, look at the airport diagram. You'd want to write down the frequencies for the airport, tower, ground. If it's an ATF, record your frequencies so you have them, and be familiar with the airport that you're going into for a circuit height, left-hand circuit, right-hand circuit, and so on. So just do your homework before showing up. I hope this video was helpful for you guys. If you have any questions, please leave them down below, and I'll be happy to help you answer them.